think it's something that's happening.
All right, so it's time we start this morning session. And the first speaker will be Luca Biferale from Rome, and he will be telling us about Lagrangian and Eulerian in statistics and intermittency in turbulence. Luca?
Thank you very much. Thank you, Chairman. Thank you. I would like to thank the organizers first, of course, for the kind invitation to this nice place. I also would like to apologize a little bit because indeed I have slightly changed the title and the content of the talk, mainly prompt from some discussion and some presentations that we have in the last few days. And so I decided that I will focus only on data, and I will present no theory, no phenomenology almost, but I just want to show you what we can say starting from data about intermittency. And I will mainly present some work that we have done recently by analyzing high-resolution direct numerical simulation from our friends in Chicago, and I will mainly focus only on one issue, that is the connection between Lagrangian and Eulerian intermittency. Of course, what I'm going to say is not only the results of my own work, but I mean I have to acknowledge collaborations or discussions are very fruitful with many people, and their names you can see here. So, good. Doesn't go on. Sorry. Okay. So this is the program of the talk. As I said, I will only speak about statistical connection between Lagrangian and Eulerian observables, and I will put myself in the simplest situation you can imagine: isotropic, homogeneous, three-dimensional turbulence. So what I'm going to say, I mean, up to me, is valid only in this very ideal case. And moreover, I will speak only about one particular phenomenon that is known to happen in both Eulerian and Lagrangian statistics, that is intermittency. And because I want to make only one point, I will speak only about intermittency as measured from structure functions. And as I said, I will mainly present DNS data, but at some point, because I will also speak about universality, that is, I would like to convince you that data are robust, that what I'm going to present you is not just the result of one data set, but it happens every time that you have a turbulent flow, I mean at least isotropic and homogeneous. At some point I will also present a nice comparison between DNS data and experimental data, and this is a joint work with many different groups, and the names of the people involved will appear in a few moments, in a few slides. And then if I have time, I will also would like to comment about what we can say about inertial range and viscous range. So first, I don't think we really need to spend too much time on this. So the focus, the idea is we have Eulerian measurements. We may also have Lagrangian measurements. For Lagrangian measurements, I mean that I seed the turbulent flow with particles, tracers, and I follow the statistics, for instance, of the velocity field along particle trajectories. And my question is, I can measure velocity increments on the Eulerian on the lab. I can measure velocity increments along the particle trajectory. Are these connected? Of course they are. I mean, they come from the same statistical ensemble, so of course they are. The problem is, can we understand their relation? And another important point that, I mean, again, has been already discussed in this conference, is that whenever you speak about Eulerian increments, you have to distinguish between longitudinal and transverse, and we will do it. So the whole and the only message that I'm going to try to convey today is that indeed, I mean, the two statistics are, at least concerning these observables, are of course connected. And a very good way to translate from one from the other is just to say that the velocity increments on the Lagrangian reference frame on a time lag tau is indeed connected to the Eulerian increments on a spatial increments r via this simple editor-over time estimate. Of course, it seems to be simple, but it is highly non-linear. And moreover, the point is that you must really use this relation not in average, but I mean looking at also at the non-trivial spatial fluctuations of the velocity field. That is, this relation is not true homogeneously in your fluid, but it's true in some sense locally. That is, if you would replace the simple Kolmogorov assumption that the editor over time goes like r to the 2/3, then, and you try to translate one statistics to the other by using this simple homogeneous relation, then things do not work. So the message is very simple. Intermittency here and here seems to be are connected, of course, and they seem to be connected by this local link between spatial and temporal scales. So I will try to convince you by using data that this is true. So what we speak, when we speak about intermittency, we know it. I mean, qualitatively speaking, it means that you measure velocity increments normalized, and you see that they PDF change. But then you want to put numbers, you want to quantify how much this PDF changes, and therefore you measure moments of the PDF. And the dimensionless number, the first non-trivial dimensionless numbers that tells you how much the PDF changes is the flatness. And we know that the flatness goes from 3 at large scales and tends to increase, and it may reach even very high values. So this is a Lagrangian measurements when you go to very small time lags. These are data from this IDNS, high resolution DNS that we did recently in Chicago. Is Reynolds lambda 600, 2048 cube resolution, 16 million particles in the fluid. This is the largest database, like speaking about Lagrangian statistics, that exists nowadays. So there are not better statistical data. This is thanks to our friend in Chicago. So the other message, the other point is we will not use log-log plot. I don't want to access intermittency globally just by making a log-log fit of something. And I want to switch from plots on 30 order of magnitudes on measuring quantities that are order 1 on all scales. So what I'm going to do is just to define, this is just a definition, the local slopes of the velocity structure function, such as I can look at how the structure functions look like by changing the scale. And the big advantage in doing that, if you have data that are clean enough, is that you switch from plotting data on 30 order of magnitudes to measuring things that are order 1. So it's what I like to call a magnifying glass. And I repeat, when you measure this thing, you don't make any fit. This is a measurement. It's an observable. You take, you go into your lab, you go in your data, you measure these things. You don't have to suppose anything, like measuring the energy dissipation or whatever you want. So this is the results on the DNS. Let's start from the Eulerian statistics. So I show you the local slopes. And as I said, I split from longitudinal and transverse. This is the results from our DNS. I mean, without cheating, I just show data without making any fit. These are the results of our measurements. This is the local slope. This is a moment p equal 2, p equal 4, p equal 6, 8, and 10. And the two curves correspond either to the longitudinal or to the transverse for different moments. These local slopes superpose exactly with the data within error bars. You see, I would like you to appreciate, I put error bars on this data because these are measurements. So I can estimate the statistical fluctuations, anisotropic components, because no data are perfectly isotropic. And so I can estimate in my measurements, what is the typical error bar that I should expect on each single point. And within error bars, these local slopes perfectly superpose with the ones published by Toshi a few years ago. The message is that, you see, I mean, now it depends, we need to start to discuss, and my statement is that there is a range of scales where within error bars, I have an almost flat behavior. This is what I call my inertial range within error bars. So the first statement is that at the almost highest Reynolds number you can reach, now there are the data from the group of Canada that are slightly largest. There is the beginning of a small inertial range where you see things that are flat, you don't have to fit anything, and then you say this is my inertial range, and then I can try to extract numbers. But the second message, which is important, that has already been discussed here, is that apparently you see longitudinal and transverse do not superpose within error bars. So I mean, at least according to this data, and these numbers coincide with what Toshi published and also coincide with what Canada showed us, the group of Canada showed us 2 days ago. If you go to moments high enough, apparently longitudinal and transverse have different, according to the data, longitudinal and transverse have different scaling. So how to extract the numbers, as I say, my procedure, I say, well, in this range of scales, I can put an horizontal line here. So I say that here I have local scaling properties which are almost constant. So I extract an exponent with an error bar, again, depending on how much big the oscillations are. And so, when this local scaling exponent is constant, I say I measure my inertial scaling. And I do it for p equal 2. You see p equal 2, longitudinal and transverse have exactly the same numbers. They must have, because there is an exact relation. P equal 4, you do not distinguish between within error bars. P equal 6, you start maybe to distinguish. 8 are separated, 10 are more separated.
So if it's in the range, the inertial range for all of the...
It's not the same. It's not the same.
Do they look?
It is optimized, no, this is just a cartoon. It is optimized in the region where it is more constant. Must not be the same. In principle, there is no reason why it should be the same. So the message, I just plot the figure big. This is the 10 order moments, the highest we can measure with some confidence, statistically speaking, because if you go to 12, this error starts to be so big that you lose confidence in your data. The message is that apparently if you go to moments high enough, longitudinal and transverse scale is different. And then the other important message that seems to me still be missed by somebody is that it is intermittent. This is Kolmogorov. So there is no way to reconcile these numbers with Kolmogorov. If anybody here is able to show me that these data are consistent with Kolmogorov, please let me know. It means that either there is a bug in my code or there is a bug in the way I estimate error bars. Then if somebody says, if you go to infinite Reynolds number, things change, well, sit and wait. Do we have data for infinite Reynolds numbers? No. So, this is the highest Reynolds we have. These are the data.
So look at the other way around, right? The lower one is the transversal.
Yes, this is the sorry.
The upper one is the longitudinal.
This is the transverse, this is the longitudinal. Yes, sorry.
And what happened to the SO3 thing you used?
We didn't do that. This is the database is too big. We can, we can't do that. We can, but it takes months. We didn't yet. So next, very quickly, now let's go how to try to fit the exponents. Right now, I make a fit. I say I have a stochastic. There are these multifractal models. I don't want to enter in which multifractal model is better. I don't think there is a ranking. It's just stupid stochastic models that are able to give you a prediction for these exponents. And because the exponents are slightly different, even within error bars, for I moments, you need to use two different sets of fractal dimensions to fit either the longitudinal or either the transverse. An open issue, of course, is if this gap is going to shrink with Reynolds. And up to my understanding, the data from Canada do not show any shrinking. But this is certainly an interesting question. And this is certainly an important theoretical question because I think there are no good reasons, theoretically speaking, to expect that the longitudinal and transverse should scale differently. But certainly they do not scale dimensionally. Kolmogorov would be here. So we use, this is the end of the Eulerian part of the talk. We try to estimate the exponents as better as we can, and we see the distinction between longitudinal and transverse. And so if we want a stochastic model to predict them, to fit them, I must use two different fractal dimensions. So now let's go into to see what happens in the Lagrangian reference frame. In the Lagrangian, so I told you measure exactly the same guys, but along a particle trajectories, and I want to check this link. Now I suppose somebody gave me the Eulerian statistics. I already know the Eulerian statistics. I did the best I could do, and so I have the Eulerian statistics through these guys, for instance. And I want to see the translation, the vocabulary. So I say, now I can predict this guy, starting from the Eulerian statistics, because I use this vocabulary. And it's a calculation of one row, indeed, to realize that if in the Eulerian, the scaling exponent, longitudinal or transverse, is given by this relation using either the longitudinal or the transverse. Then, using this translation, you have a prediction for the Lagrangian, which does not depend anymore on any free parameter. So you can predict the exponents for the Lagrangian. Of course, they are going to depend if is in this relation you use the longitudinal or the transverse fluctuation. So still here, you have if you want to use this vocabulary, because longitudinal and transverse scale differently, you have a prediction, but which depends if you say the longitudinal is equal to the Lagrangian is equal to the longitudinal, or the Lagrangian is equal to the transverse. But I would like to stress, once you give the Eulerian, either longitudinal or transverse, you have the Lagrangian without any free parameter. But the exponents are, of course, not the same. You predict them, but they're not the same because the link is nonlinear. And this is what happens. This is the nice collaboration that we had in the last few years, I would say, with a bunch of people. This is a work published recently in PRL. And this is the result of what you can measure in the Lagrangian framework about the exponents, the local scaling exponents that enters in the flatness. The flatness can be defined as the second order moment times this exponent minus 2. It's exact. I mean, it's just a definition of this exponent. And you measure this exponent again. And this is a comparison between 5 different numerical simulations, 3 different experiments from the group of, the experiments come from the group of at Riso, from the group in Lyon, from the group in Göttingen. And then there are 5 different DNS. One is from us in Rome. Another is the DNS from Chicago. Then there is the DNS from PK. Then there is a DNS from the group in Munich, from Müller. And then there is a DNS from the group also in Lyon, the numerical people in Lyon. So we measure, again, this is not a fit. We just measure in these 8 different data sets these local scaling exponents, which enters in the flatness. And what you see now, let's forget about this for the moment. This is what happens at scales which are smaller than the viscous scale. So from here on, it's just viscous scale. You see that the data, we learn many things. First, about intermittency. All data, all local slope, are very far from the Kolmogorov relation, that is 2. Again, if anybody here claims that these 8 data from different Reynolds numbers, different experiments, are compatible with Kolmogorov, let me know what is the systematic error in the experiments that in all different experiments give the same result. It would be nice to know. Second point is about universality. You see that all these experiments in this DNS have been done, I mean, trying to have an homogeneous and isotropic flow, but with slightly different forcing. I mean, you cannot have exactly the same experiment. So at large time lags here, you have different physics, but all data nevertheless collapse one into the other, taking into account of statistical and errors. The third point, well, I mean, maybe I will slightly skip the anisotropic point. Oh, but maybe I have time. The third point is about anisotropy, because one contribution to this error bar comes exactly by estimating what is the different measurements that you obtain by looking at one direction, one component of the velocity, another, or the third one. So if you would be exactly isotropic, it should be exactly the same. Because you are never exactly isotropic, you measure the spread between these measurements, and this is a way to estimate how much anisotropic you are. And this is the main source of errors here. And you see that the errors become smaller and smaller, which means that you recover isotropy at small scales in Lagrangian turbulence. That is somehow expected, but it's nice to measure also. Then let me go on, and let me just speak about the phenomenological link between the Eulerian and Lagrangian. I told you that if you're supposed to know the Eulerian, you predict the Lagrangian with no free parameters, except that you must decide if you use the longitudinal or the transverse. This is the prediction that you get if you use the longitudinal. And this is the, sorry, it's a little, because I just drawn on my PowerPoint by hand. Of course, this is a smooth curve, but I mean. So this is the prediction that you get by using the longitudinal Eulerian, and this is the prediction that you get by using the transverse. And what you see is very nice that the data, the Lagrangian data, sits in between, which is very reasonable because when you are Lagrangian, sometimes you feel transverse fluctuations, sometimes you feel longitudinal fluctuations. There is really no reason a priori to say Lagrangian should be exactly equal to the longitude, connected statistically to the longitudinal or exactly connected only to the transverse. So you can somehow use the spread between these two as an estimate of your theoretical error on predicting the Lagrangian. Then next point, just a small advertisement. Indeed, you see that the prediction goes back also, deep also in the viscous range, because you can dress this multifractal stuff, as Srini also told us yesterday, by including fluctuations of the viscous scale, and so you can go further and predict also what happens in the viscous scale. And you see that the prediction goes well also in the viscous scale. And moreover, there is also in a region where it is highly non-trivial, because you see that here you go down. You have an increasing of intermittency close to the viscous scale. The flatness becomes larger, much larger than what you would expect by looking at the inertial range. And indeed, what is nice, maybe Roberto is going to say something, or Roberto, I don't know, in their talks. What is nice is that you can also link this dip with the existence of vortex filaments. If you remove vortex filaments, this dip evaporate. You have a much in the statistics. You have a much smoother way to go to the viscous scale. This doesn't mean that. Doesn't mean that vortex filaments are really, the basic brick, but certainly there is a correlation between the way turbulence dissipate and the existence of vortex filaments. So let me just go on and finish. Now we want to push this connection between Lagrangian and Eulerian. This is only the fourth order moments. One could say, well, but maybe it works just because fourth order moments is very close to, it's small moments. You only, with this stupid connection, you only capture the most typical fluctuations. You don't capture most of the interesting statistics. So I go on and show you what you can measure with 16 million particles from this database. And with such a huge number of particles, you can really push the statistics up. And I show you the Lagrangian local slope for hyperflatness order P. So for usual flatness, flatness of order 6, flatness of order 8, flatness of order 10. And again, these are the local slopes. It's not a log-log fit. It's just a measurement. These are the previous measurements. This is just the results from our Chicago, from the database of our Chicago friends. This is the local slope for P equals 4. You see it's pretty amazingly good. And the P equals 6, you start to see some fluctuation, but yes, still, you have 5% fluctuations. P equals 8, fluctuations becomes larger, and P equals 10 becomes pretty large. But then we should start to discuss if this is still okay as a possible plateau. If one is careful, it's not that bad. So you have now the exponents for the hyperflatness in the Lagrangian domain 4, 6, 8, and 10. And you can try to see if the prediction coming from the Eulerian works well. And these are the exponents that I showed you before with the error bars. You see P equals 10 is pretty big, the error bars. This is the prediction that you would get for this exponent using the longitudinal Eulerian. This is the prediction that you would get using the transverse. Within error bars, it works pretty well. Of course, one could say, well, but maybe the trend is not the right one. Maybe indeed there is nothing. It is not true that everything is captured by this relation, and probably it's real that very high fluctuations, very intense fluctuations, may escape this. May escape this link. Still, up to the statistics that we have now with 60 million particles, you cannot really go to higher moments. Already 10 is somehow, as I show you, not so clear. The Lagrangian measurements coincide with what we would predict with the Eulerian, with this Eulerian Lagrangian Lagrangian link. So let me conclude. I think we can conclude in 4 points. The first is that Eulian homogeneous and isotropic statistics, longitudinal and transverse, in the Eulian homogeneous and isotropic turbulence, the longitudinal and transverse statistics scale differently, at least for moments high enough. Sorry, so I brought waiting from Caneta's data, but indeed 2 days ago they show us that indeed this is true also in their data. I repeat, this may be a problem for theory. I mean, I don't see any reason why isotropic and homogeneous statistics, longitudinal and transverse, should scale differently. Longitudinal and transverse are just 2 possible eigenvectors in the decomposition of the structure functions. I mean, you can make any mixing of them, and should be. I mean, I don't see why Navier-Stokes equation should know longitudinal and transverse and not any linear combination of them. So I mean, if you admit that the longitudinal and transverse really scale differently in infinite Reynolds numbers, it means that any linear combination of them do not scale. And I mean, I would like to see why and to understand why Navier-Stokes knows that transverse should be better than longitudinal or more intense than longitudinal. Yeah, but then also the transverse cannot be the one that has pure scaling, right? I mean, that's. Let me conclude and then we discuss. And then the second point I made is that there is this link, a simple link between Eulian and Lagrangian, which gives, if you consider the Eulian, gives a prediction for the Lagrangian. Of course, it may be worked on the other way. I mean, that's you take the Lagrangian and you predict the Eulerian. The only slightly asymmetry is that in the Eulerian there are 2, longitudinal and transverse, so it's slightly more complex. And that this prediction is pretty good within error bars up to p equal 10s, even if there are hints that even higher order things can change. I mean, if you look to your extrapolation properties and you extrapolate. And then the last message that is connected to this comparison between DNS and experimental data is that there is a very good overlap between many different data sets, that they all point towards the same message. Up to the neurons that we have up to now, statistics is intermittent and it is universal. Thank you.
So Luca, I'm wondering whether the difference between the longitudinal and transverse might be a resolution effect, as Srini was talking about yesterday. If you go to higher resolution rather than higher Reynolds number, will that resolve that issue?
Well, up to my knowledge, all comparisons that have been done between different DNS with slightly different resolution, you not really, if you want a small inertial range, you cannot change the resolution of factor 100. They give the same result. So my feeling is that while, of course, on the scales of the resolution, statistics change abruptly if you change the resolution, and you may have a problem. In the inertial range, things are pretty robust. Do not depend very much on the way you dissipate. After all, changing resolution is a way to make a small or larger dissimulation. And the statistics in the inertial range is pretty robust.
Okay. Going back to my 2001 paper, where
Which one?
What?
Which one?
The 2001 JFM paper with Meneguzzi and Goto, which I hope you know about.
Of course.
Okay. Where I used data from Goto and Meneguzzi and Preskowski to show many of the things you have here. One of the issues I tried to address in that paper was the claim by Mark Nelkin that a previous paper, at large scales, infrared statistics, you can't get convergence unless the longitudinal and transverse statistics in the inertial range converge. Okay?
Converge, you mean they are the same or converge statistically?
Converge statistically as
so
you
they are
get
robust.
infinite Reynolds numbers. Okay, so he has this argument. I don't know what the reference is. It's 98 or 99 something. Okay, what I found is the flaw in that argument was that the argument only works down to the Taylor microscale. So it could be the problem that you're suggesting, that you can't imagine how the longitudinal and transverse structure functions could mix and you could get an asymptotic convergence. That could be possible. That argument is only true from the Taylor microscale to the large scales and breaks down after that in the same way. Since I don't know what your argument is and I don't have his stuff right in front of me, I can't be certain of that.
No, my argument is that there is not, while we have a proof that second order structural functions longitudinal transfer and third order longitudinal transfer in isotropic turbulence must scale the same, because there is a proof.
Yes.
For high order, we don't have. So I don't expect, because we don't have either an argument that says that they should scale differently. I simply don't expect. I mean, that's because I don't see why.
Resolve the end. We'll take one short. Is it going to be short, Sergey, or?
And you have
Because then we need to move on.
what's the most plausible reason in this dissipative range that you have increased intermittency and then you have depleted the reduced intermittency when you go even to smaller scale?
No, yes, I mean.
All right,
You're all fine. You're all fine.
you're weakening.
Okay, well,
We'll
okay.
pursue the
Sorry.
discussion later.
I got already here.
Yes.